Alright guys, welcome back to work, part 2. A bicycle rider pushes a bicycle that has a mass of 1.3 kilograms up a steep hill. The incline is 25 degrees and the road is 275 meters long. The rider pushed the bike parallel to the road with a force 25 newtons. How much work is done by the normal force on the bike? How much work is done by force gravity? Rider, total work, what is the final speed of the bike at the top? Alright, so let's first just start out with the free body diagram. What we should see, there's going to be force of gravity going all the way down. And force of gravity is going to be 1.3 times 10, 13 newtons. What we should know is there's going to be a normal force going up. Force normal. We don't exactly know what that is. And then we're going to say there's a force applied going directly up the hill, which is 25 newtons. Okay? And that's what we mostly have. So, how much work is done by the normal force? So, one thing is we don't exactly know what the normal force is. So, you might want to try to figure that out first. But another thing we should know is the displacement is going 275 meters up the hill. What this also means is this brings us at a 90-degree angle with the force normal. So it doesn't matter what force normal is. We know that cosine of 90 is equal to 0. So the work done by the normal force is going to be 0 no matter what. Okay? So I hope that makes sense. Okay, let's look at part B now. So part B says how much work is done by the force of gravity. So part B. So again, work of gravity is equal to force of gravity times displacement times cosine of theta. So let's start plugging things in. Force of gravity, 13. Displacement is going 275 meters up the hill. And now the tricky part is this angle. So we know it's going up the hill, and we want to figure out what this angle is right here. So this is where it gets a little tricky. One thing we should know is that this angle right here, this is going to be a 90-degree angle, and we know the angle in here is going to be 25. So it's going to be 90 plus 25, so this angle should be 115. I hope that made sense. Let me kind of draw it again. So the force of gravity is going down like this, and then the displacement is going this way. So we know this angle is 90 degrees. And we know this angle is going to be same as the incline, 25. So it's going to be 90 plus 25, which is 115. So now let me put that into my calculator. The work of gravity 13 times 275 times cosine of 115. And I get negative 1,510.86 joules. And it should be negative because even though the bicycle is going up, gravity is trying to pull it down the hill. So it should be a negative answer. See how much work is done by the rider. So work applied is equal to force. Whoops, sorry guys. Is equal to force applied. Whoopsies. Force applied times displacement times cosine of theta. So let's plug things in. Force applied is 25. Displacement is 275. Yeah, 275 is, they're taking this really far. Cosine and the angle. So we can see that the force applied is going to the right. And we can also see that the displacement is going to the right. It's going in the same exact direction. So that means the cosine is going to be equal to 0. So if we plug this all in, 25 times 275. We see that the person does 6,875 joules of work. He does a lot of work. He's bringing this bike really far up a hill. So that's pretty hard. Alright, part D now says, what is the total work? So work total is going to be the work done by all the forces. So in this case, work of normal plus work of gravity plus work applied. Okay, and then we can just do 0 plus negative 1,510.86 plus 6,875, and we get 5,364. Okay, 5,364.14 joules. That's the total work done. We're adding up all the different works. What is the final speed at the top of the hill? So we should also know work total is equal to change in kinetic energy. And so what's happening here is work total we know is 5,364.14 is going to be equal to 1/2 mv final squared. So m 1.3 v final squared minus 1/2 m v initial squared, and the bike starts at rest, so this thing is going to be at 0 here. So now we can find what the final velocity is doing some algebra. Okay, times 2 divided by 1.3 square root. And we get 90.84 meters per second. It is flying up this hill by the end of this. Okay. All right. I'm going to move on. Hopefully that made sense. Watch it again if it doesn't. A lot of times people get tricked by these incline problems. All right, let's look at this. A 75 kilogram person slides a distance of 5 meters on a straight water slide, dropping through a vertical height of 2.5 meters. How much work does gravity do on the person? Okay. So we know what this person is going to be sliding down 5 meters. So we can figure out a few things. So we can figure out what this angle is if we use tan. Oh no, if we use sine. So if we did sine inverse opposite, which is 2.5, divided by hypotenuse, which is 5, we can find out what theta is. So I'm going to just do that right now, real quick. Sine of theta, 2.5 divided by 5, and we get this is 30 degrees. Okay? So how much work does gravity do on the person? So first of all, let's kind of draw the free body diagram. Force of gravity. Force normal. Any friction? I guess as of now, no friction. Force of gravity, so 75 kilograms, so this is 750 newtons. We know this person's going to be sliding 75 meters. And what we should know is if this person is moving to the right here, oh, I should maybe do this in a different color because that's the displacement. I'm going to do a different color. Pointer options. So this person is moving to the right, right? That means the angle between them is going to be right here. This is the angle between them. And if we know that this angle is the same as this, so this is 30 degrees, we should know that here to here is 90, so this is going to be a 60 degree angle. Okay? So it's going to be the force and the displacement have a 60 degree angle between each other. So let's try to figure this out. Work of gravity is equal to force of gravity times displacement times cosine of theta. Force of gravity, as we said, 750. Displacement is going to be going down 5 meters down the slide, and cosine, so we can see that it's going down this hill, and the force is 60 degrees away from down the hill. So this is going to be cosine of 60. And then let's see what this gives us. 750 times 5 times cosine of 60, and we get 1,875 joules. And that should make sense. It should be positive because gravity is helping to move this person down the hill. Part B, what is the speed of the person at the bottom of the hill slide? Many ways we could do this. We could actually just do potential energy is equal to kinetic energy. But for now, why don't we just do work total is equal to change in kinetic energy. And since, again, we should know that there's going to be zero work done by normal force because it is completely perpendicular doing a 90 degree angle. And we know cosine 90 is 0. So the total amount of work is just the work of gravity. So 1875 is equal to 1/2 m75 vf squared. And if he starts from rest, it's just going to be 1/2 mv initial squared, which is 0. And now let's see what vf is. 1875 times 2 divided by 75, square root of that, we get 7.07 meters per second. Okay. Oops. Last question says, if the frictional force is 12 newtons, what is the work done by the friction force and what is the total work? Okay, so part C. Work done by friction is going to be equal to the force of friction times displacement times cosine of theta. Okay, let me change my color here. So force of friction is going to be working in the opposite direction. So friction is going this way. And as it says 12 newtons. So force of friction is 12. Displacement is going 5 meters down the hill. And cosine, the angle, since it's going down the hill and force of friction is going up the hill, the angle is going to be right here, which is 180 degrees. So now I'm going to know that this is going to be equal to negative 60 joules. Okay? And that should make sense because friction is slowing down the motion. It's doing negative work on it. So what's going to be the total work after this? The total work done is going to be 1875 minus 60. So work total is going to be equal to 1,815 joules. Okay, sorry, that's a little floppy, but I hope that all makes sense. All right, let's move on to the next one. Okay, conceptual question. In the following diagram, we have two different scenarios. In the first scenario, we'll call this the first scenario right here. In the first scenario, a person lifts a box to put it on the truck. So we have this box and we lift it up and put it here. In the second scenario, a person slides a box. So we're sliding this box on a frictionless surface, incline. In which scenario does the person do less work? So think about this a little bit. What I want you to know is when in this first scenario, we're going to look at the first scenario, the person is going to be going less of a displacement. Okay? He's not going to be pushing it that far. In the second scenario, he pushes a lot further, so the displacement is a lot more. Okay? However, in the first scenario, even though he has less displacement, he has to apply more force to bring it up the ramp. So he has to apply more force. Okay? And for the second scenario, even though he's going a long distance, the force applied as he's pushing it, since it's on an incline, is going to be less. And as we know, work is equal to the force times displacement. So what happens is, even though this one they do more force, but less distance, and this one is less force, but more distance, it cancels out and does both of the same amount of work. And this is actually something that happens often. A lot of time there's a trade-off between the amount of force you have to put into something and the amount of distance you have to go. So just know that whether you're running or walking, many times you're going to be burning the same amount of calories. You're doing the same amount of work, but just one is more intense than the other. All right, moving on. All right, let's look at example number 16. A 1620 kilogram car coasts 25 meters down a hill at an angle of 6 degrees. If the total work done is 3.75 times 10 to the 4th joules, find the magnitude of the force of friction. Draw a free body diagram. Let's just first draw a free body diagram. I'm just going to draw a little box. So we have a box. Force of gravity, straight down, equal to 16,200 joules. Force normal, straight up, perpendicular up, we don't really know. Then we have force of friction. Okay, part B says, find the magnitude of the force of friction. One thing we should know at the beginning, work total is equal to 37,500 joules. Next thing we should know, the work done by the normal force. If normal force is here and the angle is here, that's going to be a 90-degree angle, meaning work done by normal force is 0. Work of gravity. Work of gravity is going to, if this angle is 6 degrees, over here, this is going to be 84 degrees. So I know this is going to be the force of gravity, which is 6,200, times the displacement, 25, times cosine of 84. And I'll put this down here, actually. That's going to be, let me just put that in, 16,200 times 25 times cosine of 84 gives us 42,334. 42,334 joules. Work of friction, we don't know what that is yet. Okay? But let's figure this out. What we know is work total is equal to work of friction plus work of gravity plus work of normal force. So that means 37,500 is equal to work done by friction, which we don't know. Work done by gravity, which is 42,334. And the work done by normal force, which is 0. So then we can figure out what work of friction is. 37,500 minus 42,334. And we get negative 4834 joules. And it should be negative because it's slowing it down from the direction it wants to go in. Now that we know the work of friction is negative 4,834, we know work of friction is equal to the force of friction, which we're looking for, times the displacement, which is 25, times cosine, and we know force of friction is going the other way, so it's 180 degrees the opposite direction. Okay, so then now we can find the force of friction. We get 193 99.36 newtons. Okay. Now it asks what's the coefficient of friction. So we should know force of friction is equal to the normal force times mu times mu. I guess we first have to find what the normal force is equal to. So we have to find what the force of gravity in the y is. So what I'm going to just do is 16,200, which is the force of gravity, times cosine of 6. And I get that the force of gravity in the y and the normal force is 16,111 newtons. So force of friction, 193.36 is equal to normal force, 16,111 times mu, and mu, 193.36, is going to be equal to 0.012. Right? Hope that worked well. One last problem. Let's see how this goes. A car of mass m coasts down a hill, incline at angle theta below the horizontal. Find the total work done on the car as it travels a distance d along the road. Include the force of friction. Okay, so this is a tough one. The only reason why it's tough is because everything is symbols, and we're not really used to that. But there's a lot of this with a lot of AP problems. Okay, so if you're doing that, great. All right, let's figure this out. So work total is going to be equal to the work of friction plus work of gravity plus work of normal. Those are all forces acting here. Already we know this is 0, so we don't really have to account for that. However, work of gravity is going to be equal to force of gravity times displacement times cosine of theta. So let's plug those things in. Force of gravity being mg. Displacement is symbolized as d, distance d, times cosine, and we're not going to use theta because that's not the angle between. This is the angle between. So what we're going to do is we're going to do 90 minus theta. Okay, 90 minus theta. That's the work done by gravity. Now let's find what the work done by friction is. Work done by friction is going to be the normal force, which is going to be mass of gravity times cosine of theta, because that's the same as the force of gravity in the y direction. So this is going to be work done by friction. So I should just say, sorry, force of friction. Let me do this first. Force of friction times displacement times cosine of theta. And as you know, force of friction is equal to normal force mg cosine of theta, and then we have mu k. Mu is going to be equal now, so we have mg cosine of theta mu times the displacement, which is d, times cosine of 180, which is just -1. So now let's put this together. Work total is equal to, I'm just going to do work of gravity first, mgd cosine 90 minus theta, minus, because this is a negative over here, mg cosine of theta mu times d. Okay, we could simplify that quite a bit, but that's going to be our answer right there. Okay. All right. And thanks for watching, guys. I hope all of that made sense. And I look forward to seeing you on the next one when we talk about power.